Hello scholars, welcome. Mr. Hinkle here. Mapping the ocean floor. This is in conjunction with exploring the oceans because in order to explore, one must navigate. And in order to navigate, you need a map and an ability to communicate direction. So as the oceans were explored, mapping of the planet improved, and that led to mapping of the ocean floor. And this is what we're talking about in today's lecture. We're going to discuss the history of techniques used to record location, that's maps, depth and speed in the ocean, how the first bathymetric maps were created, what is a bathymetric map, and then we'll understand modern techniques applied to ocean mapping. Let's give it a go. So a map is a flat representation of Earth's surface. You take Earth, it's a globe. Earth is a sphere, it's a globe. And then you project it into a square, and we can put a coordinate system on this rectangle. Basically, the current agreed coordinate system is latitude and longitude. This gets a shout out back to Claudius Ptolemy when he created his first map of around the Mediterranean using a simple coordinate system that became the basis of latitude and longitude, which are actually measurements that are calculated where your location is at on Earth relative to the center of the Earth, relative to the equator, or to an imaginary line called the prime meridian, which goes through Greenwich, New England. So there's a deeper conversation here, but what I find interesting here is that the coordinates of latitude and longitude are actually calculated relative to your location, the center of the Earth, and the equator for latitude, and the prime meridian for longitude. Great. So we have a coordinate system on a map that's 2D, and using this coordinate system, we can travel around. Now, how do you know what latitude, what longitude you're at? Well, now, GPS, of course. Easy peasy. But this technology is relatively recent. So tools that were developed in the 15th century, the Mariner's Astrolabe. Also in the 15th century, the quadrant. And then the sextant in the 18th century. And basically, this is using the location of the sun and the location of the horizon, the time of day, to calculate where you are on Earth. It's awesome. I've never used one of these. I've only read about them, seen them in books. But I can respect the mariner, the world traveler, the ocean explorer, who is using these technologies to navigate across the ocean to know where they were. Before this, we had individuals using the sun and the stars and the currents and the birds and the waves and all different kinds of techniques. But getting more formulated, right? And this leads to mapping the ocean floor. First, we have a defined grid for mapping Earth's surface. That is latitude and longitude on a Mercator projection. How fast are we going? Use a chip log. So it's a big long string that you would tie knots at regular intervals. If you've ever wondered why the speed of a boat is measured in knots, it's because it's a shout out to the original way of measuring speed, using a chip log where you would have certain knots at intervals and measuring how fast those knots would pull out of the spool. Some things from antiquity remain. Soundings, the depth to the bottom in a body of water. And it was originally done like this. 1 arm's length is a fathom. So you'd have a big long rope, you throw it overboard, it'd hit the bottom, and then you'd pull it up. 1 fathom, 2 fathoms, 3 fathoms, so on and so forth. Now the fathom is standardized to 6 feet. But you may have heard this term. I can't even fathom, or it is unfathomable, which is a reference to the bottom of the ocean being so deep that you don't have enough rope to measure all the way down to the bottom. It's unfathomable. And this was the oceans a long time ago. Their depths were unfathomable because the average depth of the ocean is around 12,500 feet, and the deepest part of the ocean is 35,000 feet. Whoa! Okay. So soundings are measuring depth, speed measured using knots, and the bottom of the ocean profile is known as bathymetry. So the ability to collect soundings, the technology increased. And let's do California, for instance. So here's the ocean. If we're going from, say, somewhere like Avila, we've got the Coast Range, and then the Central Valley. Here's me in Fresno. Hi. And then you've got the Sierra Nevadas, and then so on and so forth. This is called topography of the land surface, topography. When we think about the ocean, we have bathymetry. So if we're looking at the bathymetry of the Bay Area, we could say, here's some land, here's the San Francisco Peninsula, and then the water is here. What's underneath the water? Well, it goes down, a little bit deeper, and then it comes back up, and then we're in the East Bay, and you've got, it's pretty flat, in the Oakland Hills, like that. The distance from the top of the ocean surface, I should say, to the ocean bottom, when we create that as a map, that is the ocean's bathymetry. If you know topography, it's topography of the ocean bottom. Great. So we can create bathymetric maps, but where did this information come from? How did we get it? Okay, let's learn. So the HMS Challenger, yes, 1872 to 76, a scientific exploration where they had really long ropes and were throwing them over, collecting depth soundings. Remember, a sounding is how you see how deep the ocean floor is. And it was a big boat with long ropes, and those long ropes discovered the ocean is not flat. That is groundbreaking. If you've ever been on a boat, you can't see through the water. If nobody ever told you, nobody knew what was underneath the bottom of the ocean, you just think it was flat. I would think it was flat. In fact, maybe before this discussion right now, maybe before this lecture, you thought the ocean was flat, and that's what people thought. Why would we think otherwise? Well, because we measured it and recorded and learned that the ocean floor is not flat. So the HMS Challenger was awesome. It collected information that was the basis for comprehensive maps that led to bathymetric maps of the entire world. Okay, so during World War II, okay, so first, depth sounding was happening, even though there was no sound, but then sound was included. 1906, the development of sonar technology, sending an actual sound into the ocean column and then measuring the time it took to reflect off the ocean floor and come back. That's called a ping. Well, World War II, naval warfare was a thing, and so a ton of data was collected to map the ocean floors. It took about 20 years or so, but Marie Tharp credited with creating the first bathymetric map of the entire planet. And she did this in conjunction with her colleague Bruce Heason, although she gets the credit. Way to go, Marie Tharp. And what they found was the existence of the Mid-Atlantic Ridge, the Mid-Ocean Ridge System, one of the 3 marine provinces. And this was amazing because it was a big win for the theory of plate tectonics. It helps support this idea that new Earth is created in the bottom of the ocean at divergent plate boundaries. Crucial. So thank you, Marie Tharp, for creating this elegant, this is actually her map that she created, right? And what do we see on this map? We can see continental shelves, abyssal plains. So we see the continental margin, we see the deep ocean basin, we see the mid-ocean ridge. 40,000 miles of volcanoes that ring the entire Earth like the seams of a baseball. With this map, it brought the ocean to life. All of a sudden, understand, it was like trying to, imagine you and I were in a dark room and I was saying, hey, can you describe me in the dark? You've never seen me. And you'd say, well, I can hear your voice, so maybe I know something about you. But really, you don't know anything because you can't see. So this metaphor is on the spot, right? Hope it worked. So having this map allowed scientists to see what was on the ocean floor, and it is that knowledge that allows us to understand so many processes about how the ocean works. This is revelatory. So mapping the ocean floor is a pretty recent phenomenon, but wow, is it amazing. Now we've got technology. So we use echo soundings or pings from sonar. We've got multi-beam sonar, which casts a wide beam to measure strips of the ocean floor. We can use seismic reflection profiles, basically use an explosion and listen to the seismic waves underneath the water to get an idea of the subsurface, right? So contemporary, modern bathymetric techniques. But in order to do that, the oceans are so big. You got to have a boat that's actually doing transects over that specific area to measure it. We've only measured about 10%. But we understand we can connect the dots through remote sensing, which means it's not direct measurements, but it's satellite measurements. Satellites in the sky can measure the sea surface height, and the anomalies off of a basis can reflect the seafloor. So basically, we can use direct measurements of depth sounding and satellite information, calibrate the two to have a pretty comprehensive view of what the ocean bottom looks like. Currently, we want to bring in all of the techniques. So satellite, GPS, research vessels, seismic reflection, sonar, all of these together can help us to create models and calculate currents and tides and water temperature, sea surface temperature, salinity. This can help us to really predict where the big storms are going to hit, how they're going to hit, the effects of climate change, so on and so forth. So again, having the framework of mapping the ocean floor, let's go here, having that framework allowed us to really dive, to excel within the field of oceanography in understanding the physical, chemical, and past processes to how our oceans operate. It took a long time to get here, but we've got here, and it is great. Thank you so much. I'll see you again.